Now let's get some practice in and kickstart our study session for the day by doing this practice question under statics. So we're looking at equilibrium of rigid bodies. But first of all, what I want you to do is pause the video, pause this, look at the problem statement, get your sheet or paper, write down what you want to find, what you're given, and try to solve this on your own. So struggle through it, go through a solution, apply equilibrium, do whatever you can to get that final answer. Then you can check with my solution and go through this with me. If you get stuck, that's okay. That helps you, and that's the feedback you need. Where you got stuck, why you got stuck, and all of these questions, unanswered questions, is the right feedback you always need. So take it in. Then you can use the solution to guide you to the right steps to get that final answer. But we will do this together. Now we're told for the loaded system shown, the reaction in kilonewton at E is most nearly what? And we want to fill in the blank. So don't panic here. Don't get overwhelmed. Fill in the blank are common nowadays. So we're just going to get an answer and fill it in there. And usually you want about 4 to 5 sig figs, and we'll talk about that as at the end. Usually it's a whole number for these fill in the blank, but don't worry, get an answer and put it in there. And we know it says fill in your response in the blank. So first of all, first question, what do you want to find? You want to find here, so what we want to find is, it says the reaction at E. So we will say the reaction at E. And we know E in this case is where? So if you look at this system, it's like an interconnected system where you have point A, you have a cable, point B, you have an external point load of 60 kilonewtons, you have point C, point D, and point E. So E is what we want to focus on. We want to find that reaction. Now, another question I have for you is, what direction will this point? Is it going to point to the left, to the right? Is it going to point up, down? What direction? It will point to the left. It has to be a normal reaction, because we know a roller, for example, we're used to seeing a roller where the bottom surface is fixed, let's say, to the horizontal ground, the bottom ground, where we have a roller here. Then we know in this case the reaction would just point up vertically. Let's call it R for reaction. But in this case, we know we have that the surface, this thing is fixed vertically. It's aligned vertically where it's fixed. So it's something like this. It's fixed to the wall vertically. We have, let's say, a roller, and we have the beam here, this L-shaped beam. So the reaction must be perpendicular. So the reaction will point to the left. It must always be perpendicular for a roller. So in this case, we will say it's like a reaction here, EX. It's a horizontal reaction that goes to the left, and it will be EX. And that's what we're going to find. That's the goal. We want to find that in units of kilonewtons. It looks like all the forces are in kilonewtons, that 60 is in kilonewtons, so we're fine with that. But we want to find that, so that's what we will do. So, okay, first step, take a step back and look at this system. So it's an interesting system because it's an interconnected system as well, where you have, let's say, two beams, let's call them beams, where you have this beam BC, and you have this beam here. It's like an L-shaped beam or L-shaped member. And this would require us to, let's say, break this apart and look at find the external reactions and see how they're interconnected. What I mean by that is this. We know like this 60 kilonewtons is basically where our starting point is. Because that 60 kilonewtons will cause, let's say, tension in the cable, which we can find using equilibrium. We will have some tension in the cable. And also at the same time, we have a reaction. This 60 kilonewtons hits this beam BC. Then we know the reaction at C must counteract that to maintain equilibrium. We're looking at equilibrium of rigid bodies. External equilibrium, not internal, nothing internal, just the external body equilibrium. So once again, this 60 kilonewtons is going to hit this beam. Then the roller has to supply a reaction force. Then what's interesting is that same reaction force is going to hit this beam. It's going to hit the L-shaped beam. So it's going to hit this L-shaped beam here. Then when that hits that, we have an external force due to that reaction at C. It's going to produce some external reactions at D. And it's going to produce an external horizontal reaction at E. And that's the one we want to focus on. What this tells me is I have to consider the whole system, and I'm going to break it apart first. I'm going to break it apart into respective free body diagrams for beam BC and the free body diagram for the L-shaped beam D, let's call it DCE. Then I'm going to find the reaction at C. Ultimately, I want to determine that reaction at E. So that's a lot of words, but we will do exactly just that. So step number one, let's draw these free body diagrams. Let's break this apart. So what I'm going to do as step number one is say, draw free body diagrams. We're freeing the bodies from the reactions, the connections. So the first one is going to be BC. So what I'm going to do is call this free body diagram BC for the top member. So we know that one is like that. So what I'm going to do is just denote it as a line. So I'll just do this. For the beam, I'll just write it like that as a line. And we know, let's label the points. This will be this point, this will be that point, and those 2 points are the ends, C and B. I'm going to label it like that. This is C, this will be B. So now we know, let's go from B to C, left to right. One thing I noticed, what is this in there? So that is a tension. So tension AB. So that's going to be the tension cable in AB. So tension is always a weight. Never draw it like compressive. Tension is always a weight. A cable can only hold tension. So we know this is the tension in cable AB. Let me denote it like that. So then we have the 60 kilonewtons. Let's draw that. So 60 kilonewtons. It's going to be the external load that we're given. 60 kilonewtons. And we know the distance here. Let me label this in the free body diagram. It's going to be the 0.8 meter. So I'll just denote it as 0.8. So now let's keep going. Next, we know that at C we have something going on. We have a roller. For beam BC, we're focused just on that. We have a roller, so we'll have a vertical perpendicular reaction. In this case, it will be vertical. So we know what I can do is label that green, and it's going to be a CY reaction. CY, in the Y direction. So then let me label the distance is going to be 1.5 here. So let's label that 1.5. 1.5 meter, that distance. So now that's that free body diagram. What I'm going to do next is draw the free body diagram for the bottom shape, just to see this as a whole when we break it apart. Then we'll start applying equations. So what I'm going to do now, again, is going to be use this free body diagram. Let me draw that L shape. So we'll call it DCE, the L-shaped member. So what I'm going to do is do something like this. So we will say this member is going to be the next free body diagram, and it would look something like this. So we know that at E here, we said it has to be that horizontal reaction in the X. So what I'm going to do is just put that like this, and we will call it EX. It goes to the left. So that's what we want to find. This is the big question, right? Then we know, let's go at D. So this is D, and let me label this E here, and let me label this D. So at D, what do we have? So you see at D something that looks like a pin connection. Pin connections always has a vertical and horizontal reaction. So don't worry about the direction right now, but you can assume like a direction. We know in this case, we can say this goes to the left horizontally. The reaction at D can go to the right. But if you get the direction wrong, you'll just get a negative in your answer. That's fine. It just tells you you assumed the wrong direction. But when you proceed, let's say if you have a negative, you want to keep that negative in your next calculations. Just carry that negative if you assume the wrong direction. If you didn't, we will get a positive for the answer. But in this case, we will say this goes to the left as a reaction. We know that. Therefore, to maintain equilibrium, the horizontal reaction at D must go to the right. So we will say that is going to be that one. So we will say it's going to be dx here. Then we know dy, what's interesting, it has to go down. We will see why, but let me put that like this. I'm doing the exact direction. Again, if you get these wrong, you'll get a negative, which is just tells you you assumed the wrong direction. But now this goes down. Now we know point C. Let's just put it here. In this case, it's essentially that same location here. This point C, if we look at this free body diagram, it goes up, right? On that free body diagram, it goes up. On the next free body diagram, it has to go down. It has to go in the opposite direction. So this is something we always have to maintain and remember. The same thing is always true for beams. So on this free body diagram, it went up. On the next free body diagram, it must be equal and opposite. So it must go down. It must go down like this. So it will be CY here. But it's the same one. It's the same magnitude for that reaction at C. So now we have basically both free body diagrams denoted, but let me label the distances real quick. We know this will be the 0.7. This will be the distance of, how much is that? That's going to be 1.9. And this will be the distance of, let's label that, of that's going to be 1.2. So 1.2. So now we have this free body diagram. Let me move this a little. Let me move this here. And we know that's going to be BC. This free body diagram, let me label that free body diagram. We will call it, for the L shape, so let's call it DCE or DE. Let's call it DCE for the L shape. So now with the right free body diagrams drawn, we can apply the equations of equilibrium. So we're going to start with this free body diagram, then go to this free body diagram. We're going to start with this, then go to this one. So let's focus on free body diagram BC. What we can do first is actually solve for the reaction at C, that CY reaction. So if we can find the CY reaction, we can use this because it's going to be the same as this one. Then we can say, okay, we have CY here. This stuff is unknown, but I can apply something. I can apply the moment equation about D. It will cancel these because those hit point D, they cause no moment. So I can apply the moment about D. This I know, this is unknown. I'll have one equation, one unknown, and we can solve for the reaction EX. And I'll show us exactly that. So let's start with this one first. First step is to find that reaction using free body diagram BC. So what we will say is using free body diagram BC, we will say find that CY. So now, first step, what we will say, okay, what you can do, how would you find CY? Pause the video and try to do this. How would you find that CY? You apply moment equilibrium. So what we can do is take the moment about B. When we take the moment about B, this will be known, this will be unknown. We have one equation, one unknown. We can solve for the CY. So what we will say is sum of the moment about B must equal to 0. And we're going to assume counterclockwise rotation. Any counterclockwise rotation caused by a force times a perpendicular distance, which is a moment, will be positive. It will be positive. Counterclockwise is positive. So now let's go point by point or force by force with their respective perpendicular distances. You have the tension in AB. Does that cause a moment about B? No, it does not, right? That doesn't, because it hits point B. The line of action hits B. It causes no moment. Next one, the 60 kilonewtons. That 60 kilonewtons hits this point. It's a force, and we have, to get a moment, you have to have a force times perpendicular distance. So it hits this force times distance about B. And that would be what kind of rotation? It hits it down. It would cause rotation about that point B. It will be clockwise, so it will be negative. We have to keep that negative. So now what we will say is that 60, the moment about B due to that 60 kilonewtons is going to be negative 60. The negative is for clockwise rotation, kilonewtons, and the perpendicular distance is just simply 0.8 meters. So that is going to be that one. Then the next one is going to be the CY. This reaction does indeed cause a moment. So it's going to be up. So it would cause a counterclockwise rotation about B, counterclockwise. Then we know the perpendicular distance will be this distance plus this. So it's going to be 1.5 times 0.8. So we will say it's going to be counterclockwise. So it will be positive. And we take the CY and we multiply that by that perpendicular distance of 1.5 plus 1 plus 0.8 plus 0.8. And all of this must equal to 0 to maintain equilibrium. So now we have one equation, one unknown. Let me do the math with you here. So let me use my Casio. So I'm going to do all clear. So what we will do is going to be the 60 times 0.8. I know I'm going to move that to the right side, so it's going to become positive. And I'm going to do this just real quick so we can say 60 times the 0.8. And that's going to be that. So I'm going to move this to the right side and divide by this stuff to get CY. So now you divide by 1.5 plus the 0.8 and we get our CY. So CY, let me reduce this into a decimal. So we get about 20.869. Let's just put that 20.869 is going to be the value for CY. 20.869. So now that will be in units of kilonewtons. Everything in this case is force units of kilonewtons. Now we have CY. We're almost done. We're almost basically done. Now with that CY, we know it's going to be that value. We can move to this free body diagram and we can take the moment about D and solve for the reaction at E in that reaction that we want to find. So now let's use free body diagram. Using free body diagram BC, we will find the reaction EX. So now, what we will do, once again, what do? We take the moment about what point? Point D, and that would essentially eliminate these reactions. We're not going to worry about them. They cause no moment about D. Then we will apply the equilibrium and solve for the force times perpendicular distances and get that reaction at E. So we will say sum of the moment about D must equal to 0. We're going to say counterclockwise rotation is positive. And let's start with each component. So it's going to be CY times 1.9. And what kind of rotation does that cause? It's going to be a clockwise rotation. Force times perpendicular distance, and it would cause a clockwise rotation about point D, so it would be negative. So what we will say, it's going to be the negative CY. So let me do it negative. We know CY we already found. It's actually this, right? Let me use green when I put it. So it's going to be negative 20.869 kilonewtons. And you multiply by the perpendicular distance, which is going to be the 1.9, which is going to be that one. So we do 1.9 meters. And that's going to be that moment caused about D due to that CY. Then we can do this one, EX. So that one would be, in this case, positive. It would be positive. It would cause a clockwise rotation. If we look closely, force hits it this way. The perpendicular distance would be the 1.2. So it has to be a perpendicular distance measured to point D. So force hits it this way. It would cause a counterclockwise rotation about that point D. And that's what we will do. So we will say it's going to be positive EX, and the perpendicular distance is going to be, in that case, the 1.2 times the 1.2 meters. And all of this must equal to 0. We must maintain equilibrium. And there we have this one equation, one unknown. We can solve for EX. So let's solve for EX using our calculator. So let me do that with you here. So all clear. Let me do this. So we know what I'm going to do is take this, move it to the right side, and divide by 1.2. So my head, I already know that. But if you're just starting out, that's okay. So take it slow. Move step by step. Don't go too fast. Never ever go too fast. Especially, you don't want to make these silly mistakes for something like the FE. So you will become faster over time. Definitely. Absolutely. So we know we will take the 20.869 times the 1.9. Again, I move this to the right side of the equal sign, becomes positive. Then I divide by 1.2 to get EX. So divide by 1.2. Then we get about 33.04. That's our answer. That will be our answer, 33.04. So we will say 33.04 kilonewtons. So that will be our answer in this case. So we know what you can do is just put that. So you can just put that in the blank. So you can put on the FE 33.04 and move on. So here you can like be more precise and say, let's say I want to keep 5 sig figs, 4 sig figs, but I wouldn't overthink this. So you can probably put 33.0 and still get the right answer. So they have multiple answer choices in their program or however they create it. We know usually if you put something close to the answer or that range they have, you'll be okay. So don't overthink it. If you put 33, you probably get it right. 33.04, you'll get it right. And if you want to like take it a step further, there is like something about significant figures in the unit conversions in the FE handbook. And here the rule 6 is probably the most important. You want to retain 3 to 4 significant digits in the final result for engineering calculations, as it's stated in the FE handbook. But usually they will have a range, so don't overthink it. Put that answer and move on to the next practice question. So thank you for practicing with me. I hope you found this helpful, and I'll see you in the next video. Take care.